Very good. So let's talk about reconstructing EDSAC. And thanks to Lauren's presentation, I now have to change all my vocabulary as I go through. He's given us terms. We are a bunch of grey-haired old fogies having great fun. For some of us, reliving the past that happened before we were born. I'm barely of the thermal valve era. I think I made a battery valve radio as about an 11-year-old. I tried connecting it into the mains, and that had an interesting effect on the domestic wiring. So I decided this project I'd make my role as project manager. I was much safer, marshalling the people, the resources, and fundraising, and hopefully around the soldering iron. So let me talk about the project. Our aim is very straightforward. We want to build a working reconstruction, that one right, of Cambridge University's EDSAC computer as it was when it provided the world's first computing service in 1950-1951. And that's the picture we have of the machine from about that period. And it's an interesting question why we chose 1950-51. The machine actually ran its first program on the 6th of May 1949. So it managed to pick Cambridge to the post by a significant margin, actually, in terms of the first working digital computer. The EDSAC that ran on the 6th of May didn't have all the support for the software development testing system that actually was the thing that made EDSAC very popular with its users. It didn't really mature to that machine until 1951, and that's the machine you want to demonstrate. To capture for visitors the matter to do with computing, what it was like to use one of those early machines, and to communicate the fact that Cambridge University had software engineering sorted out nearly 20 years before the term was invented. It took the rest of the world a little while to catch up. So why build a replica of EDSAC? And this resonates, I think, with many of the points that Dora made. We wanted to celebrate an early triumph of British computer technology. Our claim for EDSAC, like all people with a reconstruction, we choose our adjectives carefully. The key one for us is practical. It was the first machine that people used to do realistic work, rather than just be amazed by the fact that it lit up and did sums. It helped 3 Cambridge scientists or scientific groups to win Nobel Prizes, and they acknowledge EDSAC in their Nobel acceptance speeches, almost as if it was a member of the team. That's Brooks and Kendrew for crystallographic analysis of hemoglobin. Before EDSAC, with pencil and paper methods, you could do simple physical chemicals and inorganic chemicals like common salt and so forth. Anything organic was far too complicated. You just couldn't get that many postdocs to do that many sums that quickly. EDSAC gave an advantage. The second one was Martin Ryle, who essentially invented synthetic aperture radio astronomy. Managed to nick the large German radar dish that became John Bank, and that gave Bernard Lovell his advances in radio astronomy. Cambridge didn't have one, so Martin filled a field with beam poles with a 6-inch nail on top, collected the data from each of them, and then used EDSAC to process that data to simulate a dish the size of the field that he filled, and got better resolution. That's the whole basis of synthetic aperture mechanisms. Again, without EDSAC to crunch the numbers, that couldn't be done. The third example is Andrew Huxley, who used EDSAC to simulate some of the signaling in the neural systems in our heads. And so the machine changed the face of science in Cambridge. It moved it on from what could be done with pencil and paper methods, and where science could only advance if you could find an analytical equation to express your results. Provided you could find a numerical way of computing the results, you were in business. And that's the origins of much of modern science, which is done on computers in silicon. Indeed, my partner today is using computers to simulate the growth of cancer tumours and the therapies to remove them, and all that is taking place in the computer. It's much faster than doing it in real biology. And one of the drug companies, AstraZeneca, has 2 drugs out in the market, have essentially been done almost entirely in computer, very limited clinical trials, because they know so much about what's going on. So this role of EDSAC as a computer that gave us insight into science, I think is very important. And we have quite a number of the early programs that we can look at to demonstrate that. So we're going to celebrate the triumph. We wanted to better understand the heritage and to enrich the archive of material we had about EDSAC. One of the things Maurice Wilkes, the man at Cambridge who led the project, said was everything you need to build a copy of EDSAC is in the university library. He died a few years ago. If he hadn't done, I'd been around his house knocking on the door and saying, well, where did you hide it all? It is a very incomplete record if you actually want to build a reconstruction. We particularly wanted to revive disappearing expertise and understand the technical challenges faced by those pioneers. And that has been a challenge to us. None of the people who worked on the machine unfortunately survived, so we couldn't tap into their expertise in the way that the baby reconstruction team were able to do. We were definitely too late in starting the project. Fortunately, in the volunteer team, I have a number of balding and grey-haired gentlemen who had the misfortune to do national service in the Royal Air Force and or to work for early computer companies like Ferranti, who worked on slightly later version of thermonic valve machines, and so they had the expertise to understand valve circuits. Others of the team who are younger have had to learn that from first principles and talking to our more elderly experienced colleagues. And we have one member of the team who actually used the machine as a student. So he's our expert on questions like, what colour were the walls? Is this colour? How did you do that? And our aim is to provide a useful exhibit at the National Museum of Computing that can be part of the education programmes. The benefit, I didn't expect educational resources, because it's physically so large, you can walk around it and say, that's the accumulator, that's the multiplier, that's the store. And so it's a very large, opened up computer that has all the ingredients of the modern machine in very simplified form. And actually it's quite a nice teaching aid if you're trying to explain what's going on inside the machine. And it runs slow enough. Well, you've had it all working, you can probably run around the machine about as fast as it can. So, the achievements of EDSAC: first practical machine, all the other adjectives we share with other projects. The key thing is it was built by Wilkes to provide a computing service. He ran a part of the university called the Mathematical Laboratory, which was a central part of the university, much like the library, a resource shared by all departments, and its role was to provide technology that would help people in university compute. And in the early days that meant hand calculators and differential analyzers and so forth. Well, Wilkes got to hear about computers when he came back to the university after wartime service in radar, and heard about some of the early work going in the US. He realized Cambridge needs one of those, and he made strenuous efforts to learn as much as he could about American developments, come back to the UK, and build one for Cambridge. EDSAC was built fairly quickly. The design is fairly conservative. He didn't design a machine to be the biggest or the fastest. He wanted to get it working and see how people used it and learn from that experience to design what might come next. And in many ways, for a lot of people who are kind of in the Cambridge tradition, EDSAC 2 is the pinnacle of Cambridge design, where a lot of things that were learned from EDSAC 1 were taken into EDSAC 2, and new ideas like bit slicing and microprogramming and a whole host of other things came along. It's important from the point of view of software. There is no way of reading binary into EDSAC unless you choose to write a program to do that. You feed in your programs in assembly code, which is read in by initial orders, translated by initial orders, and if your assembly code uses subroutines, you feed those tapes in, and it's all automatically laid out in store and glued together for you without you having to worry about it. And so the machine had a programming language, and that language was designed to make it easy to assemble software, to reuse other pieces, other people's code as subroutines, and to link those together. And indeed, a lot of the effort once the machine was working was to build an extensive library of subroutines for all the numerical calculations the machine had to serve. Unfortunately, much of the software is preserved because Wilkes wrote a book about it in 1951, published by Axel Wesley. And like every computer science programming book since then, they essentially use their assembler and their library as the example code to explain how it worked. So it transformed science. Roughly speaking, EDSAC will run at about 650 instructions a second. That's not very exciting compared to your iPhone or even your Apple Watch. But compared to a postdoc, it runs 1,500 times faster and doesn't have to go to the laboratory and doesn't have to be eating sandwiches. However, there's an interesting contrast with the other early machine that faces us in the gallery where we're building EDSAC around the museum. That's the which is the world's oldest preserved working computer, which also was designed quite conservatively. It runs a lot more slowly than EDSAC will, but it was designed to run for very long periods. So they could leave it doing calculations that might take days and the machine wouldn't fall over. EDSAC doesn't have that property. From the operational logs, it's clear it did break down and there were engineers resident, and if you got a few hours out of the machine, you thought yourself to be doing well, but if a few hours at 1,500 times what a postdoc can do, you're still ahead of the game. And indeed, early users, they will quite often run programs 2 or 3 times to be absolutely sure they were confident in the results. Most failures did result in a hard stop, but there was a possibility of there being failures in the way the store operated that could introduce errors. And certainly expecting it to run 24 hours a day was not expected. And finally, of course, the other part of the story is Lions essentially took EDSAC as the design for the core of Leo, the world's first business computer. And they tidied a few things up in their system, and reading the accounts of how Leo was designed, we can reverse engineer from that what weaknesses were in EDSAC. If they changed this, why did EDSAC? What was the problem in EDSAC, and how would you build a circuit with that problem? Quite interesting. So, and the forensic analysis that's gone into the project, led particularly by Chris in this respect, has just absolutely been great fun. Essentially, the primary documentation has been photographs. There is written documentation. It is incomplete. It is incorrect, and sometimes completely misleading. And so, wherever we can, the question has been answered by, can you demonstrate where that circuit is in one of the photographs, and can you date the photograph? There are places where we've had to invent things, but we've kind of deferred doing those until we understood all the rest of the machine, so we kind of knew what the house style and the house approach was. So reasonably confident that we were going about designing the gaps, so to speak, in the data we had, in the same way the Cambridge team might have done. I think for Chris, who's led that design effort, that was an interesting challenge, because he's very schooled in Manchester methods. Occasionally I hear Chris muttering about Cambridge mutter mutter. In the same way I used to hear Wilkes talking about Manchester mutter mutter mutter. I think they're all actually great friends, but there are house styles. EDSAC is a completely ordinary computer. It's a serial machine. The way you think about it is essentially there is a although they call them buses, it's not a bus in a modern sense. That's another track of machines. They use language that sounds familiar, but it's subtly different. And so, although EDSAC has an input bus and an output bus, it certainly isn't tri-state. If you don't disconnect things or you put signals on at inappropriate moments, bad things happen. But essentially, the flow is, there are delay line stores, tanks of mercury. Instructions are pulled out of those and go into a machine called main control, where you have the current instruction or order. You have the sequence control tank or program counter that tells you where the next instruction is to come from. Main control decodes the current order and opens and shuts gates, taking input from the input bus through some functional unit and putting it on the output bus as required. The arithmetic unit operates as an autonomous subsystem. You give it a number and say, add this to the accumulator, or multiply the accumulator by this. Output to teleprinter, input from paper tape. The storage system is itself circulating, it's the delay line, and so data is going around the store. You can only take data into the store at the right moment when the word you're addressing is about to go into delay line, and you're going to take data out of the store when that data is coming out of the delay line. So there's quite a lot of quite tolerant synchronization in there. And in terms of debugging the machine as you're building it, it's quite a challenge because you've got layers of wheels within wheels within wheels. And sometimes to get round to seeing the same signal reasserting itself, you've got to wait quite a long time for everything else to happen, and that can make debugging challenging. We have to build ourselves some interesting debugging aids. So the memory of the original machine were mercury delay lines, tanks full of mercury with a piezoelectric crystal at each end, one to transmit and one to receive. I won't say very much more about the memory technology because there's a talk about that tomorrow. The key point is we felt we couldn't reproduce this. Everyone thinks it's health and safety. That's not actually an issue. When I investigated the health and safety requirements, it's an issue when you fill the tanks, but the Cavendish Physics Lab in Cambridge said they'd help you do that. They've got the appropriate facilities. The real gotcha is operationally, every couple of years they had to drain the system down, redistill the mercury and clean the tubes because of corrosion and interactions. The second gotcha is the precision of these tubes, and particularly the alignment of the end fittings and the crystals, has to be very, very precise. Otherwise you get echoes and other effects in the tube that destroys the transmission. We didn't feel we could meet that level of engineering requirement. Our suspicion is, for EDSAC, a lot of tubes were made in this central machine shop at the engineering labs in Cambridge, and they picked the best 64. We probably couldn't afford to do that. And unfortunately, Tommy Gold, who was Wilkes' expert in how to make these things work, wasn't available to us in the way he was available to Wilkes. So we decided to substitute nickel delay lines, a technology that came into being during the lifetime of EDSAC, although it was never used by EDSAC. We are fortunate that Wilkes recognised that this was the best of a bad bunch as far as he was concerned with memory technologies. He could use this, he could use the just recently invented Williams tubes from Manchester, but those weren't really a proven technology in his mind at that time, or he could use some sort of rotating magnetic drum that was more established from some of the card reader systems. He went for the delay lines because he knew of them from radar, but he designed the interface between the delay lines and the circuits that do the recirculation, so they were neutral to what this technology might be. And that has helped us tremendously, because in commissioning, what we've actually used are little transistorized circuits that we plug into the back of the circulation system. So we have a modern semiconductor store that's completely reliable and can be trusted. In the final machine, so we're using nickel delay lines, and there's a whole story about the research that had to go on to recover the technique for how you manufacture those. The physics is well documented, but how they were put together is quite a mystery. And every inquiry seemed to terminate in whichever company it was that made delay lines, there was someone called Fred in the back of the workshop who knew how to do it. And when Fred was gone, that was the end of the knowledge. There's some practical hand skills in how you connect things together. So, the EDSAC's a serial machine, that's a natural consequence of using the delay lines. However, the machine can't be entirely serial, and the most complex areas of the machine are where you actually need to look at some of the data in parallel. So all the arithmetic is serial. But if you want to address store, or you want to decode an instruction, you actually have to capture the whole instruction code as a parallel series of digits, so you can put it through a decoder tree. And similarly for memory, the way the memory works is there's a part of the machine called the coincidence unit that has a counter that's essentially free running, and that's telling you which word in memory is the one currently coming out of or going into, depending on the point of view, the delay line store. And so to address store, you assert the address, the coincidence unit flips the signal up when the address you assert matches the counter, and then you know it's time to open the gates and move data in and out. And I think there's a whole interesting discussion to be had about, given the complexity of all of this, how much saving is there actually because the rest of the machine is serial? Not a huge amount. Although the accumulator is double length and it's 70-something odd bits, that will be quite a lot to replicate as a parallel system. So how do we go about building the replica? The key question is authenticity. We didn't have a complete blueprint, so our aim was be consistent with photographs and contemporary records. We started off with the view that we would use period components and circuits when available and suitable. Suitable turned out to be quite a useful get-out clause, and I'll say a bit more about that as we go through. Where we couldn't find period components, we'd use functionally equivalent modern components otherwise. And to cut to the chase, essentially all the passive components, capacitors and resistors, we use modern ones. People gave us boxes of lovely old tatty resistors and capacitors, and you just find they've drifted away from their nominal values, and so they're not very useful. And from our point of view, provided it is a 10 ohm resistor where the circuit diagram said 10 ohms, then we think that's good enough, even if physically it looks quite different. And it does have an impact on the visual appearance of the machines. And where we were filling in gaps, we wanted to understand what were the EDSAC principles, rather than just diving in. And in particular, when you're doing this, you really have to forget all the new stuff you know. You have to remember they didn't know about phase lock loops, for example, haven't been invented yet. And that's quite hard. So we had a technical description and logical design outline from the university's archives. We don't quite know who wrote it, we don't quite know when they wrote it. We think it was written by an Australian visitor, probably about halfway through the construction phase. And so it's mostly correct, but not completely correct. We've discovered in hindsight. Well, that's what we believe. We may, of course, misinterpret it. A lot of original photographs. Some aspects of the machine are published in papers. The mercury delay lines actually are quite well written up. There are written recollections of the pioneers, but most of those recollections were captured in the late 1990s, and many of them blur EDSAC 1 and EDSAC 2 in their memory because it was a long time ago. We found a cache of 20 circuit diagrams when we were about 2 to 3 years in the project. Those were very helpful because they confirmed a lot of our guesses. They were diagrams of the machine at the end of its life, and where there were differences, by thinking about the differences, it kind of confirmed that some of the circuits we replicated that we thought weren't the best way of doing that job were indeed the way they probably did it initially, because we saw in these later drawings, the drawing had a revision number and had a better circuit for doing that job. Our challenge has been, in some cases, matching the changes in the drawings to the timeline from the photographs. And as the machine ran for 10 years and they kept playing with it, so we needed to understand how it changed as it went through. So let's go through the various levels of replication. Mechanical design was helped significantly by the fact there were surviving chassis. They called them panels in EDSAC. So we could measure this. We drew it up using computer-aided design. We didn't know how many different types of chassis there were in the EDSAC when we started. So we essentially designed a generic shelf and then put an overlay of holes and things to be punched in it. And we went to a local engineering company in Cambridge, Cambridge Precision Engineering, who would make these things for us. In EDSAC's day, there was a mechanical workshop in the computer lab. It would probably have taken a skilled sheet metal worker at least half a day, if not a day, to manufacture one chassis, all the punching and bending and whatever. This machine stamps out, drills, punches, whatever, 12 chassis on an 8x4 sheet in a matter of seconds, and then round and spray move. So we literally, for the first batch of these, went to the factory, saw the sheets of metal go in the machine, bang, crash, folded metal in the spray move, quiet lunch and took them home. I'm sure Wilkes would have loved to have had that. Up to the next, there is one little gotcha in there though. EDSAC metalwork was wartime steel. Wartime steel was quite bendy. Modern steels aren't like that. I have this challenge in another one. I'm also involved in aircraft restoration, one of which is a 1940s seaplane. You can't get old-fashioned bendy metal. Modern metal is far too strong and stiff. And so we have to be a little bit careful with the bends on the EDSAC metalwork, because the modern metal would split if you bent it too tightly. If you just run a little tool line down the inside of the curvature, the right thing happens. And fun enough, I use the same trick on the aeroplanes too. Right, so next level up, logic design. You need to know how EDSAC worked in detail. So we had drawings, but evidence lots of redesign, lots of logic not explained. So really the first key piece of work done by one of our volunteers, Bill Purvis, was to build a logic simulator. And he took as his input these kind of logic diagrams in this mystery report written by goodness knows who, goodness knows when. But when he turned most of this into a logic simulation, it sort of mostly worked, which gave us a lot of confidence in these diagrams. This is what we now call the arithmetic unit. It shows the two halves of the accumulator, shifting units, half adders, complementers, collators. So how the machine does arithmetic, and most instructions are concerned with arithmetic in EDSAC, is pretty well defined by that diagram. So you get pictures like that, and these often helped us understand what individual chassis might do, because often these blocks corresponded to a chassis. Alongside those, there was quite often helpful timing diagrams that told you how many pulse intervals apart these various units were, i.e. what delays were in the machine. And that helps you in the design of main control that has to poke these things at regular intervals. It tells you when it's got to waggle the appropriate signal. So putting all that together, we built a simulator called ELSI, EDSAC Logic Simulator, Interactive Editor, I think is what ELSI stands for. ELSI can run EDSAC programs very, very slowly, but more importantly, it produces out these charts of waveforms. So we know the machine is correct, and these waveforms are potentially of use to engineers in commissioning, because they should see the machine reproducing something like that. To make a long story very short, it was clear the EDSAC pioneers weren't bothered about noise in the way that modern digital engineers are. They weren't particularly bothered about what levels were, providing they were different, and pulses didn't have to be very square. It depended whether you wanted an edge or a level as to how hard they were trying to clean things up. So if you're looking at EDSAC on an oscilloscope, you never see anything as pretty as that. It's all much spongier and fluffier and wobbly. But there you go. So that takes us to electronics. It was built by people whose background was radio and radio engineers. They thought in terms of waveforms, not in terms of logic ones and zeros that engineers of my generation were brought up on. And they thought about analog circuits to achieve digital effects. So all their thinking was in the analog domain, though the effects were digital. They hadn't flipped into being digital designers in the way that just one cycle machines later everyone was. Digital logic in valves is quite expensive. An AND gate eats up 6 valves, that's 6 holes in your chassis, and a third of a chassis gone. You can get about 20 holes along a chassis. So lots of space-saving shortcuts. You didn't clean things up unless you had to. You didn't decouple things unless you had to. You basically negotiated with the next person down the line and had a bit of a tussle about whose problem it was to deal with mucky signals. And we've essentially been going down that same path with the Reconstruction. Fortunately, they did have a library of common circuit elements, and that did surprise me, because even at my time in Cambridge, the tradition was each PhD student was left to design their bit their way, provided you met the interface requirement that goes into's and that goes out of. How you did your own thing was your own business. So the fact there were common circuits was quite surprising. And some of the projects I was associated with, like the Cambridge Ring, I can look at some of the circuit boards and say, that's a Herbert piece, that's a Martin Johnson piece, that's an Andy Hopper piece, because we had quite different design philosophies. Fortunately, obviously, Bill Rennick, who was his chief engineer, imposed some discipline, and that's helped us a lot. There were some circuit diagrams. This one turned out to be a huge snare and delusion. It calls itself a flip-flop. This is actually the monostable that Doran talked about. You notice there are no component values. You're just assumed to know that. Again, to make a very long story short, and the story literally only ended last Wednesday, depending on what values you set here, you either get a monostable you can flip quite rapidly, but it doesn't remember for very long, or you can flip it gently and remember for a long time. And in most of the machine, you know which of those two cases you need. In one part of the machine, you want it to flip rapidly but remember for a long time. And there is no set of values that we found to make that behave. And we've had to switch to a later circuit that we found on some of the diagrams that is a passive bistable. And having done that, when we went back through the photographs, we convinced ourselves, reasonably convincingly, I think, that there was a bistable even as early as 1951. And we spent a year having the same probably experience that pioneers did in wondering why this monostable circuit wouldn't work in that one situation. So how do we get from the logic to the chassis? Our great hope was on some of the photographs, you could see little labels on the chassis, so that was going to be easy. We just blow the photographs up, don't we? And then the label comes more and more into view, a bit indistinct, but you keep going, and you get to there, And I can read that that says coincidence unit 3, but that's because I know from other sources that was coincidence unit 3. You're kind of getting down to the resolution of the grains of silver nitrate on the glass plates. So that one didn't work for us. And we had great fun trying to write various kinds of image processing programs to see if we could extract meaningful data out of those. And there are quite a few chassis that are hidden from views. That didn't help. This is what a 1949 chassis looks like. The grey hair in the room will remember that capacitors were that size and resistors were these big chunky things. That decision to use modern passives in the interest of having reliably functioning circuits makes ours look less dense. Visually, it's not too much of a problem because this is a chassis upside down. And when you look at the machine from the front or around it, you're going to have to lean underneath to see this. So that's a bit of invisible cheating. So the fact we lost some authenticity there doesn't upset us too much. All the valves sitting on the valve bases where the thing is the right way up, those are correct valves and correct sockets and all right. Other little things, interfacing technology was tag strips and solder, and they originally had tag strips on the side for power distribution. We thought that was a bit dangerous, so we used modern plugs and sockets. There's been a tension there between essentially health and safety aspects for us in commissioning the machine versus what you do as authentic replication, the original. And we thought having volunteers with electric burns on their arms and fingers was probably not the right authentic thing to do. Most of the valves we were able to get commercially as new on stock, but we couldn't get the valve holders. The valves in EDSAC were used in radar systems well into the 60s, and because most of those systems are bought on government purchase, government buys lots of spares. You buy spare valves, you don't buy spare valve holders because they're part of the metalwork. And so we had to get a whole batch of them made, and there's a whole story there, you can ask that in questions. And quite a few things you can't get in the shops anymore, like various kinds of coil delay lines, tag strips and so forth. Those are all lovingly handmade, mostly. The memory tanks, there's a talk tomorrow. So the key thing is risking cost. I didn't say the cost of filling the tanks is about £160,000 if you could buy commercial mercury today. The other issue we know they had with EDSAC was the temperature stability of the mercury delay lines. So we've gone for nickel delay lines. They match the electrical interface of EDSAC without us changing anything in the store drivers, to use one phrase for them. We use semiconductor shift registers to get off the ground very quickly. That's one of our delay lines, built by one of our volunteers, Peter Linson. He'll talk about that tomorrow. A huge amount of research, starting with what's the wire made of, how do you support it, how do you coil it without introducing attenuations and reflections and so forth. How do you make the little fingers that put the twist into the wire to send the ones and zeros through? How do you roll those to the wire without eating all the way through the wire and so forth? A fascinating sub-project in its own right. There were some posed photographs in the original EDSAC team. Wilkes on the right with Bill Rennick, his chief engineer. This is clearly a very posed photograph. When I was a young researcher in the computer lab, several of these people still there as senior engineers, and I never saw them wear suits. But I thought since they're wearing suits, I should wear one today for this talk. This is my scruffy bunch of volunteers. Again, a somewhat posed photograph. So where are we? We started in 2010 with a feasibility study. A charity was created so we could go fundraising. We raised, I think, slightly over £250,000, helped by some founder donors who put some very large checks in the hat first time round, which is nice. We had a second round of fundraising, recruiting volunteers, mostly through CCS, but also people turning up at museums saying, can I be part of this, and personal networking. 2 years of forensic engineering research, and then starting design with a lot of prototyping of circuits and evaluating them. Construction starts in 2014. Commissioning starts in 2015. By commissioning, I mean people starting to join things together in different parts of the machine. Final third round of fundraising, just like a startup, we have an A, B, and C series. But IPO sometime next year. And where are we now? I hope that we'll be running programs of some sort by late summer, early autumn this year. From the threshold of that, and that by very early next year we can complete it in the sense that the machine can be handed over from the commissioning team to the operations team, whoever that turns out to be, probably the same people. So, wrap up. Present status, we've built 135 of the total of 142 chassis required, and we understand the remaining 7. Main control is almost working. That's where the monostable that needs to be a bistable circuit held us back. Arithmetic is working. It was working in Cambridge. The guy who designed that built it all and tested it all in his workshop in Cambridge, and then we heaved it up to Bletchley Park, and hopefully it will be working again once we wire it back together. We know all the memory system is working. We know the delay line stalls for registers are working, and we've made the I/O devices work using FPGA. And hiding behind this, the final part of the story, is the penny has dropped that there are sufficiently few control signals, and given most of the data is travelling serially, we could put a fast machine, and this FPGA might well be the right thing to build, hidden inside the machine that's monitoring all the signals. That would help us with diagnosis if it goes wrong, and potentially could switch out the bits that have gone wrong and just simulate them. So we may be able to keep EDSAC running, even with great chunks of the machine down, until engineers can come in and fix it, because there aren't actually too many wires you have to chop to put in a modern system that knows how to do the job. But then it wouldn't really be EDSAC, or maybe it would, or maybe I need to go and read Donna's paper again. Thank you very much.
Thank you, Andrew. Our next speaker has been referred to through constantly today, and that's Mr. Chris Burt. Chris was responsible for really the starting project at CCS, and that was the Reconstructing. The replica of the Manchester Replica. Andrew spoke about the use of Edsite in the museum when it's finished. What we wanted to hear from is someone who's had experience of running the machine after the actual construction is complete for a length of time in the museum, and really Chris is the person for that. Now I'm praying Chris is going to behave himself this time, because we are, I'm conscious, running